Hello Math 200 students. I'm going over a particularly difficult problem on homework 3.2, number 13 here. So we're using Bayes Theorem, and Bayes Theorem is this. It's the probability of A given B is equal to the probability of A times the probability of B given A over the probability of A times the probability of B given A plus the probability of A prime. That's the complement to A. So not A times the probability of B given not A. Alright, so it tells me in the problem, it gives me a pretty good bit of help by saying what A and B, how to define the events A and B. It says let A be the event the person is infected. So A, person infected. And B is the event person tests positive. So let's see if I can identify some of these probabilities already. The probability of A, probability that a person is infected, is equal to, my particular problem says 1 out of every 150 people. So 1 out of 150. Alright. So I'm also noticing down here that I had I wrote something wrong. It's not the probability of B times A, it's the probability of B given, that should be a vertical line, B given A, not A prime, which means the opposite of A. So I can now say the probability of B testing positive given that you're infected, B given A. The probability that you test positive given that you're infected, B given A, is equal to, I think it tells me that up here too. It says a test used to detect the virus in a person is positive 80% of the time. So it'll be 0.8 when the person has the virus. That's B given A. And 5% of the time when the person does not have the virus. So that's the probability of B given not A, it tells me, is 0.05 in my problem. That's the false positive. Alright, then it says, using Bayes' theorem, when a person tests positive, determine the probability that the person is infected. Alright, so we're looking for the probability of positive given that we're infected. Nope, it's the opposite of that. It says when a person tests positive, determine the probability that they're infected. So we're looking for the probability of being infected given we test positive. So that's the probability then of A given B. That's going to equal, according to Bayes' theorem, it's going to be the probability of A, which we've already said is 1 over 150, times probability of B given A, which we've already said is 0.8, divided by probability of A, again that's 1 over 150, times the probability of B given A, again that's 0.8, plus the probability of not A. Well, the probability of not A, let's go back up here, probability of not A, probability of A prime or complement is the opposite of this. It's 1 minus 1 over 150. 1 minus 1 over 150, which is 149 out of 150. Probability that you are not infected is 149 out of 150. Kind of an interesting thing that we're doing this problem right now, and come to think of it, with this whole virus thing going, hysteria going on. Probably that you got a much greater chance of not being infected than being infected. So 149 out of 150. That's probability of A not prime is 149 out of 150 times probability of B given A prime. The probability of B given A prime, we've already said that's the false positive, that's 0.05. So we just do that calculation in our calculator. And let me pause this and do that calculation. So that the actual probability that you are infected, even if you test positive, is actually 0.097. Okay, 0.097. So the less than 10% chance of actually being infected, even if you do test positive. Alright, so now let me try to do part B. When a person tests negative, determine the probability that the person is not infected. Okay, person tests negative. So we're looking for the probability So this time, I think it would be beneficial if we define the A so that it will fit this theorem again. Define the A part here as not infected. Okay, not infected. Because last time we defined A as is infected. So this time we're going to define it as not infected. And B is going to be, can you guess what B is going to be? It's going to be test negative. Alright, because last time it was test positive. Okay? So let's see if I can do this. The probability of A not being infected is 149 out of 150. Probability of not A this time would be being infected, which would be 1 out of 150. Alright, probability of B given A. So that you test negative given that you are not infected. This part's confusing, but so again, this is testing negative given that we are not infected. And that's given, if I look here, if we test positive 5% of the time when the person does not have the virus, that means we test negative 95% of the time when the person does not have virus. If they don't have the virus, they test positive 5% of the time. That means they're going to test negative 95% of the time. That's 0.95. Alright, I think I'm ready to roll here. So the probability of A given B is going to be, just following this formula up here, 149 out of 150 times 0.95 over 149 out of 150 times 0.95 plus probability A prime here is 1 out of 150 and probability B given A prime. Okay, I haven't done that one yet. Let me come up here and try to do it. Probability of B given A prime. Let me think about that. That means we test negative given that we are infected. test negative, given that we are infected. All right, look right here. Positive 80% of the time when we have the virus. That means we're going to be positive. That means we're going to be negative 20% of the time when we have virus. Okay, that's again just the complement of this. So that's test negative when we have the virus. That's this right here. That's 0.2 in this case. So times 0.2. And that is my whole formula. I just need to type in my calculator. And then try to get it 0.999. So that's when we test negative, the probability that we're not infected is really, really high. 0.999. If we test positive, the probability that we are infected is still pretty low. So that's a really interesting problem. I just love Bayes Theorem. I just think it's so interesting. And it's especially interesting now, right? Very, very relevant and coincidental that we would have a problem like that. And thinking about what our world is dealing with. I'm sure there are lots of scientists, medical people that are using this kind of probability stuff when making decisions about what our society is doing in this virus. I know this is a difficult problem, but I hope you're able to see what I've done here and take your numbers and apply what I've done to your problem to get right. Good luck on that.